After this, let's move on to Laue equations. Laue equations, just like Bragg's law, are another representation of the diffraction condition. But this representation is useful for single crystal diffraction, finding out the structure of a single crystal, and it gives us a lot better sense of the geometry in which the diffraction condition is satisfied. So let's discuss that. The diffraction condition, that is delta k equals g vector. This may be expressed in another way to give the Laue equations. The geometric representation may be better appreciated from these equations. So let's take the scalar product of the real axis vectors a1, a2, a3 with delta k and g. So if we take a1 dot delta k on this side, so we are taking the scalar product of a1 from the left. Also on the right hand side we will do that, and that will give us twice pi v1 just by the definition of g. Similarly, a2 dot delta k, that would yield twice pi v2 from the definition of g, and a3 dot delta k similarly would give us twice pi v3. And these equations have a simple geometric interpretation. The first equation, that is this one, if we consider this tells us that delta k lies on one cone about the direction of a1. Similarly, the second one tells that delta k lies on a cone about the direction of a2. Third one says similarly the delta k lies on a cone about a3. How is that possible? How can we satisfy all these three conditions? The three conditions can be simultaneously satisfied if these three cones intersect and give us a common line. So delta k must be that common line. So three cones intersecting and giving us a common line, that's rather a stringent condition. It's not quite common to occur. And it requires a bit of more brainstorming in terms of geometry to be able to appreciate this condition. Let's work out the Ewald construction to better appreciate this stringent condition. So here I am drawing a sphere, although I am drawing on 2D, so it looks like a circle, but I am trying to draw a sphere centered here, and I'll draw some lattice points using blue color. So let's put one lattice point here, one lattice point here, like that. These are reciprocal lattice points. I can have more lattice points like this, similarly spaced, and so on. So this lattice will certainly extend to infinity, and we have the incident vector, wave vector, this, that is k. The scattered wave vector is this, that is k prime. This is the origin, the angle between them is twice of theta, and delta k equals g. So how did we construct this? I have just explained you how I drew the picture. This is not the construction. The construction is the points on the right hand side, that is this side here, are the reciprocal lattice points of the crystal, and the vector k that is drawn along the direction of the incident wave. So this is the direction of the incident wave. We have made this vector end at one of the lattice points. So the origin is chosen in such a way that k terminates at one of the reciprocal lattice points. Now we draw a sphere of radius of this magnitude of this k vector, that is k equals twice pi over the wavelength of the light that we are shining on it, or whatever kind of wave. It can be electronic wave or neutron wave, whatever. So the radius of this sphere is the absolute value of k, and we draw that sphere about the origin. Now a diffracted beam would be formed if the sphere intersects at any other point in the reciprocal lattice. So here we have considered one point where the sphere intersects. The sphere may intersect, say, somewhere here. It may intersect on some point outside this plane. So this is just one plane of the sphere that we are looking at. The sphere is bigger, the lattice is three-dimensional, so it may intersect in somewhere else, and those are the delta k values for which we will have delta k equals g, and this diffraction condition will be satisfied. The Laue equations, all three Laue equations will be satisfied, and once everything is satisfied, we will have non-zero scattering factor, non-zero scattering amplitude, and that is the situation where we would get some diffracted wave from this situation. So the stringent condition is clearly explained by this Ewald condition, Ewald construction. So this construction is very helpful in understanding, geometrically understanding and making a picture of the diffraction condition in our mind.